We'll start today with a practice problem. Go ahead and pause the video and see if you can determine which of these four compounds matches the mass spectral data. When interpreting mass spec, the most important thing is the molecular ion peak here with a mass of 112. In a question like this, what you can do is check the mass of each of these individual compounds and make sure that their molecular mass adds up to 112. A, B, and D add up to 112. C only comes in with a mass of 108, and so it's out. Then what you'll notice is the gaps. So from 112 down to 69 is a gap of 43. From 69 to 41 is a gap of 28. So the degradation pattern that we expect to see is something falls off with a mass of 43, and then something falls off with a mass of 28. When you're looking at A and B, those are both esters, and the common degradation points in a mass spec are in between the carbonyl carbon and the singly bound oxygen. So that bond is going to break, and the mass that we lose should correspond to a mass gap that we see in the mass spec. A methyl group and an oxygen, methyl weighs 15, oxygen weighs 16, that would result in a peak fragment. We'd see a big peak at M minus 31, and then you'd see the gap of 28. That's not what we see for this spectra, so A seems like a low probability. In letter B, we have a vinyl group with 2 carbons and 3 hydrogens. That weighs 27, plus the oxygen gives us a mass of 43. If we were to clip this bond right here, we would lose 43 units of mass, which is exactly what we see right here. And then the carbonyl group would fall off to lose another 28 units of mass. So the degradation pattern matches B much better than it matches A. Finally, with letter D, there are a variety of different degradations that would occur here, including the loss of the alcohol to produce a carbocation that would have resonance delocalization. So I would expect to see a peak with a mass loss of either 17 or 18, depending on how the alcohol fell off. Or with the aldehyde, you'd lose one of the units of mass from the hydrogen and then 28. So D would have a rather complicated degradation pattern in this, and it would not have a 43 gap. There's nothing that weighs 43 that would readily fall off, and you've got a lot of other things that would fall off, so I would expect D to not look like this and be rather messy. So based on the common degradation patterns that you see for esters, where they clip off the carbon-oxygen single bond, and then you lose the carbonyl group, B is the only one that really matches this particular mass spectrum. We're going to start off with a new chapter, chapter 21. This is all about Aldol reactions, which are a unique classification of chemical reactions, and we'll start with sections 1 through 3. Even though we're calling these Aldol reactions, and you should recognize the ALD, which is the root term of aldehyde, everything we're saying is also applicable to ketones. So treating aldehydes and ketones as a group, this whole chapter is going to go into the type of chemical reactions that aldehydes and ketones can do. And the chemistry is based on not the carbonyl group. So the last few chapters we've been focusing exclusively on the carbonyl group. In this chapter we're going to start looking at the positions adjacent to the carbonyl group, these alpha positions right here. So the most interesting part of a molecule is generally not given a Greek letter, and then you call anything that's adjacent to that most interesting position. You label that with a Greek letter, alpha, beta, gamma. So there are 2 alpha carbons right here, 5 alpha hydrogens, then there's 1 beta carbon and 2 beta hydrogens, and then the gamma position here, which we rarely need to talk about. Most of the chemistry is going to occur at the alpha position, with some interesting things that occur at the beta position from time to time. The interesting thing that happens at this alpha position is hydrogen abstraction. And so we're going to start thinking about this alpha hydrogen right here as if it were an acid. So if I were to draw these 2 hydrogens out, or let's start with these 3 hydrogens over here and draw them out here. If you add a base to the system, we'll just refer to this base currently as generic base, It's going to have a lone pair and a negative charge. The base is going to pull off one of your 5 alpha hydrogens. These electrons will drop down to make a pi bond and push out here onto the oxygen to form an enolate. The enolate will look like, in a little bit of space I have here, 1, 2, 3, 4, 5. I have 5 carbons, 1, 2, 3, 4, 5. The enolate will involve a carbon-carbon double bond right here with the oxygen carrying the negative charge. The driving force for this reaction is the strength of the base coupled with the fact that the oxygen ends up with the net negative charge, which from an electronegativity perspective is expected. Like if there's going to be a negative charge to go around, we expect the oxygen to take that on. And what ends up happening is we have a carbon-hydrogen bond that normally has a pKa in the ballpark of 60, which is incredibly high and extremely weak. Because of the ability of the alpha hydrogens to be removed and produce an enolate conjugate base, their pKa drops down into the region of 16 to 20, which is a much more reasonable pKa in terms of we can find bases that will effectively remove these hydrogens from the alpha position. Here's another diagram that tries to illustrate this chemistry. This aldehyde right here, in the presence of a base, can be deprotonated at the alpha position. So here's the carbonyl group. The alpha carbon is the one that's adjacent to it, and it has 1 alpha hydrogen. With hydroxide as a base, you can pull this hydrogen off to produce the enolate. Water is your conjugate acid, and if you'll notice, the pKa of my aldehyde is 15.5 at the alpha position. The pKa of my conjugate acid, water, is 15.7. Water at 15.7 is a slightly higher pKa value, therefore slightly weaker, and therefore equilibrium will favor the formation of products. Not by a lot, but by enough. So this tells us that hydroxide is able to effectively remove a hydrogen from the alpha position of aldehydes. If we look at this table right here, it's trying to show you the ketone structure or the aldehyde structure for the bottom two. It shows you what the conjugate base enolate would look like, and then tells you the pKa of the original ketone or aldehyde. In order to deprotonate these things effectively, ideally you would use a base whose conjugate acid would be higher than 19.3 or 18.3 or 16.7 or 15.5. And the point of this is that by the time you get down to these aldehydes, you can generally effectively deprotonate them with the conjugate bases of alcohols or alkoxides, such as hydroxide, methoxide, ethoxide, tert-butoxide. All of these bases that we've seen in the past are able to effectively enolize your aldehydes. They're also not bad at producing enolates out of your ketones, because as long as your pKa gap is less than about 5, in other words, if an alkoxide base has a conjugate acid pKa in the ballpark of 14 to 16, that means it can deprotonate enough acid with a pKa in the ballpark of 20 that Le Chatelier's principle can do the rest of the work. So in conclusion, to a lot of information about acid-base chemistry that you may not remember very well, we can essentially turn all of these aldehydes or ketones into enolates using alkoxide bases. And even if equilibrium doesn't necessarily favor the formation of the enolate, we can couple this with a chemical reaction that removes the enolate, drives the equilibrium forward through Le Chatelier's principle, and we can kind of power our way through the fact that alkoxide bases may not be very good at forming the enolate, but if we remove the enolate, Le Chatelier's principle can do the rest of the work. So in this chapter, we're going to see a lot of alkoxide bases ripping hydrogens off of carbons at the alpha position in aldehydes and ketones. That's going to be the first step in a lot of our chemical reactions. So in the previous chapters, we've been looking over and over again at the SNAC mechanism. This is no longer SNAC mechanistic chemistry. but instead it's we're going to form enolates. And so we'll talk about formation of enolate will usually be the first step in our chemical reactions. So let's consider a simple ketone. I'm going to start off with cyclohexanone. And we'll put a double bond on the carbon to the oxygen right here. We'll make that oxygen just a little bit bigger so it's easier to see what's going on. Okay, this cyclohexanone has 2 alpha carbons, left and right side, and on those 2 alpha carbons are 4 alpha hydrogens. So here's one of my 4 alpha hydrogens. Here's another alpha hydrogen. We'll draw in the other 2, alpha hydrogen and alpha hydrogen. In the presence of an alkoxide base, so we'll use an oxygen here, and then we'll just call this R. We won't be too picky about this. Normally we just use ethoxide and methoxide. We'll see hydroxide. Just in the laboratory, if you can use hydroxide, it's really kind of convenient because it's cheap and readily available. Problem is the solubility of hydroxide is pretty low in most organic solvents. Whereas if you tack an R group on here, then it has a little higher solubility. So methoxide and ethoxide are more expensive and a little easier, though, to solvate in the laboratory. So none of these considerations matter to us on paper. So what we'll do in the first step is we'll form the enolate right here. And the enolate formation always involves the base coming over here, grabbing a hydrogen, the electrons drop down, and then swing up onto the oxygen. So this is our enolate formation mechanism. Let's move this over just a tad, and we're going to show the product of this reaction. Okay, we now have a double bond right here, and we don't have a double bond on that oxygen anymore. I'm going to redo my lone pairs, but I'm going to put a negative charge on there. So here is the enolate. Now, clean that up just a tad. There we go. The enolate has a resonance structure. Where's my resonance arrow? Oh, there it is. Okay, the enolate has a resonance form. Let's move this over just a little bit more so I can make room for that. And resonance structures are both representations of the same compound. And in the resonance form, you can actually take one of these lone pairs from the oxygen, push it back down to make your carbonyl. So I'm just going to take one of these lone pairs and drop it back down right there to make a double bond. And then in order to do that, I have to break the carbon double bond and push those electrons out onto the alpha position right there. So these 2 structures right here, I'll put the negative charge out on that carbon. These are resonance forms of each other. And here's our resonance brackets. Now, any resonance structure that is reasonable, and these are both reasonable resonance structures, we can either put the negative charge out here on the alpha carbon, or we can put the negative charge on the oxygen. Any mechanism that you show that produces one resonance structure would be equally correct if you produced another reasonable resonance structure. So instead of showing the deprotonation mechanism where the alkoxide, or whatever base happens to be, pulls a hydrogen off and drops those electrons down to an alkene to make an enolate, you can also just, and you'll see the textbook does this from time to time, it just pulls the hydrogen off and just leaves them right here on the alpha carbon. And that will produce this carbanion resonance structure. Since both resonance structures are reasonable, then you can show the mechanism either way. You either show the mechanism all the way to the formation of the enolate, or you can be kind of laziest possible correct mechanism is to just leave those electrons hanging there at the alpha position, because that is another appropriate resonance structure. Most of the time, I will show the formation of the enolate. So I'm just going to go back here in my mechanism, and we'll just leave it here at the enolate. So I'm going to get rid of this resonance structure, but occasionally you'll see the carbanion show up, and that's perfectly acceptable. So this is the more common way of us showing this. Now, what happens if we don't have a symmetrical ketone? So for example, let me take off one of these hydrogens right here and replace it with a methyl group. And if we replace that hydrogen with a methyl group, what we end up with is an enolate that is either has an alkene that is connected to 3 carbons, so that would be a tri-substituted enolate, or if instead the alkoxide comes over here and pulls the hydrogen off the other side. So we'll come over here and grab that hydrogen. That arrow got a little out of control, but oh, that's just too ugly. Let me fix that just a tad. We'll swing that down just a bit. Oh, whoops. There we go. It'll drop that hydrogen down, and then instead we'll get the enolate formed on the other side. So these electrons will drop down here, and then we'll push those electrons up right there. So I'm going to show these as 2 different colored pathways so we can consider them simultaneously. Like this, we'll make these, shoot. Okay, so now we're going to consider either the black pathway or the blue pathway. And we'll color this one blue. And then the enolate that we get out of this, we'll flip this horizontally, and we'll leave the methyl group on this side, and we'll have the hydrogen over here. And we'll make this blue. Okay, so this black pathway or the blue pathway. This represents a kinetic versus thermodynamic consideration. If your alkoxide comes in to the more sterically hindered side, and that methyl group produces some steric hindrance, if your alkoxide base has to fight through the methyl group, it's going to be slower. So the black pathway represents a slower pathway. On the blue pathway, the alkoxide is able to pluck a hydrogen off that does not have as much steric hindrance because there's just another hydrogen right there. So this represents our kinetic pathway down here. Now, just because there is a kinetic pathway, it doesn't always mean that there is a different thermodynamic pathway. Thermodynamic pathways reflect the lowest energy product. Kinetic pathways reflect the fastest product. And that refers to the activation energy. So the blue pathway right here would happen more easily. As that alkoxide comes in, it would be faster for it to grab this hydrogen on this side because it doesn't have to push through the methyl group. When you identify something as kinetic, it doesn't necessarily mean it's not also thermodynamic. Most reactions we run, the fastest product pathway will also end up being the most stable overall pathway. In this case, they are different. Here is a pi bond between 2 carbons that is bound to 2 other carbons. If we ignore the oxygen, then I would refer to this pi bond as a di-substituted pi bond. This pi bond up in the black pathway is a tri-substituted pi bond, if we're ignoring the oxygen, which is fair to do because I'm ignoring it consistently for both compounds. Di-substituted alkenes are less stable than tri-substituted alkenes. So this means that I end up producing a kinetic product if I go one direction and a thermodynamic product if I go the other direction. So this is a case of kinetic versus thermodynamic. Here I've laid it out a little differently because I'm going to talk about energy diagrams. So the black pathway is moving to the right, that's the thermodynamic product. The blue pathway moves to the left, that's the kinetic product. If you just look at our starting materials here, they have some arbitrary energy state. They start off at some energy level. This is an energy diagram, so whoa, the writing tool gets a little crazy. So let's do it differently. So this is energy, or as my high school physics professor abbreviated it, energy. Okay? So if the higher up I move on the y-axis, the more energetic the reaction process will be. And so if we go to the thermodynamic pathway, what I'm stating is that the energy activation barrier will be higher because we've got to push an alkoxide through that methyl group, but our overall energy state will produce a more stable compound. And therefore, if we push the other direction, the kinetic pathway, we're going to go through an energetically lower transition state, but we won't drop as far down in energy because the di-substituted alkene here is it's not as stable. So we'll change this to blue. Oh wow, I keep accidentally moving my color scheme around. All right. So again, this is our starting material, our reactant right here that we started with. This is the thermodynamic product, and this over here would be our kinetic product, like this. Now, if you heat a reaction up, the molecules will go back and forth and back and forth. They will explore all possible pathways. At high temperature, you produce a lot of equilibrium conditions, and all the molecules just kind of wander across the entire energy diagram. And this is most of the time what we're doing in the laboratory. You guys turn your hot plates on, you let the reaction reflux, and all the molecules are highly energized, and they start bouncing back and forth between all these different energy states. And then you turn the reaction temperature down. And as soon as you do that, the molecules start to lose energy. And what happens is they get trapped behind the largest energy barrier. So everybody's moving along, plenty of energy, and then all of a sudden they start losing energy. And the first trap that will occur is this trying to get from the thermodynamic product back out. That energy hill, as you turn the temperature down, starts to become a barrier that nothing can cross. And what ends up happening is most of your molecules, as they're moving back and forth across these energy states, will get trapped in the thermodynamic product. So this is how, under high temperature, for long periods of time, if you run a reaction, then you can eventually get everything to fall out, or most everything to fall out, as a thermodynamic product. So the condition is the reaction has to be reversible. Molecules have to be able to move across this energy diagram. And so if we want the reaction to get trapped in the kinetic product, we need to either keep the temperature low or remove the possibility, you can't remove possibilities, you can decrease the probability of reversibility. The way we do that is we don't use alkoxide bases. These alkoxide bases are not strong enough to drive the equilibrium forward, and so the alkoxide base itself allows for a reversible reaction. Anytime we're forming these enolates using an alkoxide base, you should expect the thermodynamic product to end up as your major product. The other base that we use instead is a base that is so strong that once it pulls the hydrogen off, these things don't unenolize, so they'll stay in the enolate form. And the types of bases we use here are the amide bases. Now, we just talked about in the previous chapter how an amide is a nitrogen connected to a carbonyl group. And unfortunately, as chemists, we also use the amide to refer to a nitrogen with a net negative charge. So very different looking structures. An amide base does not have a carbonyl group. It's just a nitrogen that carries a negative charge. And yes, that's exactly the same word we use to describe a nitrogen adjacent to a carbonyl. So to figure out which one we're talking about, generally you have to keep track of the context. If we're using them as bases, then we're talking about this type of amide. If we're doing some type of snack mechanism, then we're talking about the other type of amide. Sorry about that. It was thoughtless of us as organic chemists. The problem with the most common amide is solubility. So what they did instead is they took this amide and they started adding alkyl groups to it in order to produce a higher solubility amide. So this would be dimethyl amide. And then we decide, well, if we're going to have a negative charge, you can't just buy a box of negative charge. So we're going to put that with a positive charge as a conjugate charge. So we're going to match this. So you buy a box of lithium dimethylamide. But this doesn't have quite enough solubility, so then what they came up with was lithium diisopropylamide. So this right here, whoops. So we're going to put two isopropyl groups on either side of this. And this actually does there's a huge win in terms of its functionality, because it does a couple of things. The two isopropyl groups right here give it increased solubility, and they also hinder this nitrogen from reacting like a nucleophile. This nitrogen with these large sterically hindering groups right here is sterically hindered enough that it won't go and attack the carbonyl carbon, but it's not so sterically hindered that it can't pluck a hydrogen off. And this also has a much harder time pushing through the methyl group to get to that hydrogen, and instead will come over here and rip the hydrogen off of the open position. So this base, and this is commonly referred to as LDA, lithium diisopropylamide. LDA will rip a hydrogen off of the less sterically hindered side. Sorry, I was showing that base abstraction on the product. It can't get to that hydrogen very effectively. It can get to that hydrogen, and once it takes the hydrogen off to produce this enolate, you can't take that hydrogen back. This thing is such a strong base that it's one and done. So we end up with kinetic product. So the take home on all of this is enolate formation can vary based on kinetic versus thermodynamic considerations. So then I wanted you to show the mechanism for the base catalyzed enolate formation of 2-methylcyclohexanone. And that's exactly what we did right here. Which enolate is favored under kinetic conditions? Well, the enolate that's favored under kinetic conditions is the one that pulls the hydrogen from the less sterically hindered side and produces the alkene that is the least substituted. Kinetic control is favored at low temperatures with a very strong base, lithium diisopropylamide. Which enolate is favored under thermodynamic conditions? That's the enolate that pulls the hydrogen from the harder to get to side, which produces a higher activation energy, but results in a more stable overall alkene. Thermodynamic control is favored at room temperature with weaker alkoxide bases. This is something that's a little different from the past. In the past, I said that if it was room temperature, we generally expect it to go kinetic. In this particular case, in order to go kinetic, they usually cool this down to negative temperature Celsius. So here, thermodynamic, you have to keep track of. It needs to be at least room temperature or higher, and then we're going to run it with a weaker alkoxide base. Kinetic control is at a low temperature, usually negative degrees Celsius, with a very strong base like lithium diisopropylamide or other types of amide bases that are suitable for the particular chemical reaction. So we look for nitrogen bases here and oxygen bases right there. All right, at this point you should be asking, great, we can make enolates, what do we do with them? And this is referred to as aldol addition and aldol condensation reactions. Those are the two big reactions we're going to look at in this section. So under basic conditions, aldehydes will react with other aldehydes to produce an aldehyde alcohol. So here are two aldehydes reacting with each other. They're both the same, and we're going to find that that actually makes things a lot easier. We're reacting them with a hydroxide base, and we're going to end up producing an aldehyde and an alcohol. Rather than say aldehyde alcohol, we call them aldols. And that works really nicely until we get to ketones, where ketones will produce what we should be calling ketols, but we still refer to as aldols. So we almost made things easier for students, and then we decided to mess it up at the end. Okay, the second aldehyde may be the same as the first. That's what we're seeing right here. I have two similar aldehydes react with each other. We're going to look in a second at what happens if the aldehydes are not the same, and that's typically referred to as a mixed aldol addition. And then if we try to run this reaction with ketones, usually the equilibrium will favor the reactants and we don't get a lot of product. There are some ways of cheating the system to get ketones to do the chemistry, but that's why this is typically referred to as an aldol addition, because the original chemists that kind of figured this chemistry out were exclusively using aldehydes. So let's look now at the mechanism for this reaction of an aldol addition reaction. In the first step, we're going to make an enolate, and that is going to be a recurring theme throughout this chapter. So once you make the enolate, then that enolate, so we pull the hydrogen from the alpha carbon. There were two hydrogens to choose from, and it didn't matter which one I pick. I end up making the enolate. This is an equilibrium condition because usually the alkoxide will only produce about 50% enolate and 50% unreacted. In the second step, the enolate then unloads through the nucleophilic alpha carbon. So the whole purpose of making these enolates is to produce a nucleophile at the alpha position. So the electrons slide down to reform the carbonyl carbon double bond. Then these electrons push over here into the carbonyl carbon of the other aldehyde, and we end up with our tetrahedral intermediate. This may look pretty familiar to you from the snack mechanism, but we're not actually substituting anything here. This is an addition reaction, so it doesn't necessarily follow the same features the steps as a snack mechanism. You have to memorize these as kind of a separate unit of understanding. So the first step is the formation of the enolate, and then the enolate unloads into the electrophile. Final step is we have to regenerate our hydroxide base, and so this hydroxide picked up a hydrogen to become water in the first step, and this alkoxide right here is going to rip the hydrogen off of the water to get to our final product. Here is the aldehyde and the alcohol. We added two aldehydes together, so that's where we get the term aldehyde alcohol addition or aldol addition. If you have aldehydes in this reaction, then equilibrium would favor the formation of the aldol. If you have ketones, then equilibrium doesn't favor the formation of the product, the ketol product, and so that's why we typically run these reactions with aldehydes. It is often difficult to stop the aldol, to stop at the aldol point and not get the reaction to continue. So when you get to this product right here, usually, well, it can keep reacting if you add any heat to the system. So if we want to stop at the aldol, we usually have to keep the reaction very cold, like -Celsius. If you want the reaction to keep going, then you just run it at room temperature. And what happens at room temperature or hotter is you have a hydroxide in the presence of an aldehyde, and there's another alpha hydrogen right here. So remember that the very first step in our mechanism overall was to pull a hydrogen off of the alpha position. When we're done with the aldol addition, we now have an aldehyde again with an alpha hydrogen, and the hydroxide is going to continue to pluck those hydrogens off. Putting this carbon adjacent to it with an electron withdrawing OH actually makes the second hydrogen easier to pull off than the first hydrogen. That's why it's very difficult to keep this reaction here at the aldol. Usually just keeps rolling. In this step, the hydroxide will pull the second alpha hydrogen off. We form another enolate, and then the enolate unloads into itself to push off a hydroxide. So we use an equivalent of hydroxide here to start the chemistry, and the molecule itself kicks off a hydroxide, and that allows the hydroxide to continue to be catalytic. This is referred to as an alpha-beta unsaturated aldehyde. So let's unpackage that word. So here's the aldehyde, the carbonyl group with a hydrogen attached. There's my alpha carbon. There's my beta carbon. Unsaturated means that we've removed some hydrogens at the cost of a pi bond. So the term unsaturated fats means that you've removed hydrogens from your fats and instead left them with pi bonds. Unsaturated aldehydes are the same concept. So you can stop the reaction at low temperatures and at this point and not allow the aldol to continue to react to produce the unsaturated aldehyde, or you can let the reaction warm up and then it runs through until you get to the unsaturated aldehyde. I used to show this mechanism incorrectly. This is the correct mechanism, and I used to think that you could just take the hydroxide, pull the hydrogen off, and flop the electrons down to the right, knock off the hydroxide, skip the enolate intermediate, and go all the way to product. And then I was reading through a research paper where the authors actually explored the thermodynamics of this reaction, and they demonstrated that the energy diagrams show that it goes through the enolate. So one of your homework questions is showing you that energy diagram and just asking you to show the mechanism for the full aldol. They call this a condensation reaction. So this is not, aldol addition is the first step, and then we get rid of the water in the second step to produce an aldol condensation. So that's your job in homework question number 3, is just to show a full aldol condensation mechanism, which are the last 2 slides kind of tacked together in a single mechanism. So then what happens if we put 2 different aldehydes together? So this is referred to as a mixed aldol addition reaction. And here we have 1, 2, 3. So this is propanal, and this is a 2-ethyl butanal. We're going to react those 2 with each other to produce 4 different potential aldol addition products. So, for example, this product right here means that we made an enolate out of the blue molecule and it plugged into the black molecule carbonyl group. That's how we got this aldol product. Over here, this product is if we made an enolate out of this molecule and then it plugged into itself, a similar molecule, that would give us this product. Here, if we made an enolate out of this compound and it plugged into itself, we get this one. Or we could make an enolate out of this one and it would plug into that carbonyl group. And this is a mess. Like, we've got all kinds of products all over the place. And so this is why we usually don't have a mixed aldol addition reaction. We don't like to put two aldehydes in solution that are different, throw hydroxide in there, and then roll the dice just to see all the products that we're going to get. The yield here would be horrible, depending on which one of these you wanted. So if this is the compound you wanted, it wouldn't be more, you probably have less than 50% of your molecules would react in this fashion because they would be distributed through all these other combinations of enolate and aldehyde that could potentially exist. So then how do we solve this problem? Well, the easiest way to do it is to use one aldehyde that can't enolize. So what I mean by that is you can't pull a hydrogen off of the alpha position of benzaldehyde because it only has one alpha position carbon over here. This alpha position is occupied by a hydrogen. You can't pull that off with a base. And there are no hydrogens connected to this alpha position. So there's no way to get an enolate out of benzaldehyde. So when you add this to the reaction, then this thing will never become the enolate. If you use a ketone as your other compound, then it will enolize, and so ketones don't mind being turned into an enolate, but they don't like you pushing carbons into their carbonyl group. They don't act as very good electrophiles. And let's go back to that mechanism and talk about why that is. So here's, we form the enolate right here, and then the enolate pushes into a carbonyl group. If this carbonyl group right here has another alkyl group, then the product of that reaction has a bunch of steric issues. So notice how this ethyl and methylene carbon over here on the right-hand side in the product, this hydrogen is sandwiched between a lot of things. And if you make that an ethyl group or even a methyl group, it's going to have some steric conflicts there that are going to end up pushing your equilibrium back. So the result is that ketones don't react well as electrophiles in these aldol condensation or aldol addition reactions. So if you enolize one of your ketones, it's unlikely to push into another ketone. So this is a mixed aldol condensation reaction where the mixing doesn't cause any problems because this thing can't make an enolate and this thing will only react as an enolate. It won't accept electron density. So we enolize this acetone, forms the enolate, it plugs into this aldehyde, and then we go through the condensation step to knock off the hydroxide. So let's show the mechanism for this reaction instead of me just waving a cursor at it. All right, so I have all the pieces in place here. Here's the benzaldehyde, here's acetone, and I have one of so there are two different alpha carbons, the carbons on either side of the carbonyl group, and each of those alpha carbons has 3 alpha hydrogens. I've only shown one of the potential 6 alpha hydrogens because they're all the same. My alkoxide base is going to come over here and pull a hydrogen off of the alpha position. Benzaldehyde, its alpha position would be this carbon right here, and it does not have any hydrogens. All 4 of its bonds are already occupied, so the only alpha position that's available is for my base to come over and pull that hydrogen off. You can either just drop the electrons directly onto the alpha carbon, or I'm going to push them up onto the enolate because that is traditionally how we show that. It's not more or less correct to show it this way, it's just more common. So we're going to end up enolizing our acetone to form the acetone enolate. I imagine it has a different name than acetone enolate, but that'll work for now. Convert structure to name. There it is. Prop 1-ene-2-olate. Yeah, acetone enolate. That's easier to say. Okay, so the acetone enolate is in the next step is going to unload its enolate. So we just drop the electrons right back down to reform our carbonyl bond, and now through the alpha carbon, this thing is going to reach out as a nucleophile. And this is where it's going to react with the benzaldehyde. So let's flip this thing horizontally, put it right there. These electrons, which are unloading out, we'll start up here, are going to push into that carbonyl carbon right there. The electrons will pop up onto the oxygen, and the product of that reaction is, it's not an aldehyde alcohol, it's an aldehyde oxide, which we don't have a fancy name for. Let's see. All right, so we took that negative charge away. I have to rearrange these a bit. Just made that bond right there at the cost of my pi bond, but we did get the carbonyl back, and then this carbonyl got broken, and we pushed those electrons up onto the oxygen. And it has a net negative charge right here. Okay. Clean that up just a tad. Okay, in the next step, this oxide is going to go pick up a hydrogen. We used an alkoxide base in the first step, and it needs to be catalytic, so I'm going to get that alkoxide back. So I'll go out here and pick these electrons. These electrons will go pick a hydrogen off of the conjugate acid. We'll want to draw that hydrogen so we can show its bond. Let's see, that arrow is now needs to be pointed down. I think I should play background music when I'm walking through these mechanisms this slowly. Okay. Now, if the temperature is low, it will stop at this point. Let's go back and check to see. Nope, temperature at 30 degrees Celsius is slightly elevated relative to room temperature, which is usually around 22 to 25 degrees Celsius. And my product shows that it's not an alcohol. It's not an aldol. It's actually the aldol condensate. Condensation just means you removing water from the system. So the way we remove water is by getting rid of the OH group, and then this hydrogen is also going to get plucked off. So I still have alkoxide present in solution. That alkoxide is going to come over here and pull off the alpha carbon. And this was the point I just tried to make, that you could, these are incorrect, the arrows I'm about to draw, so you could push the electrons down this way and pop off the hydroxide, and then in a single step you would end up with your final product. And so now this is gone. Everything I'm showing you is not quite correct, so you don't have to write this down. I'm just showing you what I used to think happened. Whoops. So this is the way I used to think the mechanism would run, and then I found out that that is not consistent with the data. So instead of pulling the I'm going to keep this because this is our final product, but instead of pulling the hydrogen off and getting the electrons to push off the hydroxide, the electrons instead will come over here and form another enolate. And the reason for that is just the highest probability pathway, sort of. Breaking a pi bond is easier than breaking a sigma bond. And so this is what ends up happening. And it's confirmed by the energetic studies of this mechanism that we end up producing another enolate. And then it's this enolate that unloads, just like enolates do. So the unloading of an enolate is pretty similar every time. The electrons drop down from the oxygen's negative charge, cause the pi bond to break and to push into something else, and then that something else usually loses a bond. So this is common for enolates unloading through something. And then that's how we end up getting our final product right there. So here's the full mechanism for a mixed aldol condensation reaction. Just another comment on this mechanism. Again, anytime you have a mixed aldol condensation reaction or mixed aldol addition reaction, you need to ask yourself, why did it only go this way? Why did I only make the enolate out of the acetone? And why didn't I make an enolate out of this aldehyde? And the answer to that is, well, this aldehyde didn't have any alpha hydrogens, so you couldn't make an enolate out of it. The second question then is, why didn't this enolate right here, so I'm going to grab this, instead of attacking the aldehyde, why didn't it just attack another equivalent of acetone? So why didn't this happen right here, where one enolized acetone would come over here and push into an unenolized acetone? And the answer is that it is very difficult to push an enolate into a ketone because the result of that has a lot of steric hindrance. So if we show what the result of that looks like, I'm going to use this as a template. Let's show the arrow. And I'm going to show an equilibrium arrow to remind us that it's not that this isn't happening, it's that when it does happen, it just undoes it. It just unwinds. So here, if I take this enolate and try to push it into another ketone, the resulting product looks like this. And there's a lot of steric issues here. All these methyl groups are bumping into the acetone enolate that I just added in. And so the highest probability is that these electrons will just come back down and knock the nucleophile back off again. So it just pushes it and undoes the chemistry. Takes us right back the other direction. So yeah, this is going to happen. One of these acetone enolates will plug into acetone instead of benzaldehyde. But when it does, the resulting product just kind of unwinds itself and gives us back our acetone and our enolate. But instead, if you push it into the benzaldehyde, then this compound is less likely to unwind itself and more likely to pick up a hydrogen and keep rolling through the system. So the take-home is that ketones make very poor electrophiles, especially compared to aldehydes. An electrophile is the thing that's receiving the electron density from the enolate. So you can enolize a ketone, but you generally can't plug one enolate into a ketone, and that's what allows this reaction to produce high quantity of a single product instead of giving you the 4 different products that we saw earlier with a mixed aldol reaction. This slide reiterates the point that I just tried to make. And so here is a ketone, and we're going to react it with another ketone to try to form an aldol addition, which technically should be a ketol addition at this point because you have a ketone alcohol. When you try to make this compound, it tends to unwind itself, and so equilibrium does not favor the formation of a ketol. We end up with 2 separate ketones. So what if your life goal is to try to get 2 ketones to come together? Well, if they're intramolecular, then that can happen. So this reaction right here is an aldol condensation reaction involving ketones. So notice how we started off here with 2 separate ketones, and when we're done we end up with a ketone, and then at the alpha position and the beta position there's a pi bond. So that is going to happen through alpha-beta condensation, or the aldol condensation reaction. This sodium carbonate would just be a catalytic base in this case to pull off a hydrogen off the alpha position, then it plugs into the carbonyl group, and away we go with the chemistry. So the mechanism is exactly the same. And if you run this internally, then you can get ketones to do this. Catalytic hydrogenation at the end is just a little decoration you add to produce this compound. I'm not even sure why I included the catalytic hydrogenation. I believe I stole this from your textbook. The textbook probably pulled it from the literature where somebody went through an aldol condensation of internal ketones and then hydrogenated it to get to the final product. Another way of dealing with mixed aldol condensation reactions to avoid getting a whole bunch of product is to do it stepwise. So here, again, we're going to look at lithium diisopropylamide. This was that kinetic base that I showed you before. And one of the things you can do is you can take, in a mixed aldol condensation, you can take one of your aldehydes or ketones, react it stoichiometrically with LDA, and then add in another aldehyde in a second step. So let's look at the mechanism for the reaction of 2-methylcyclopentanone with LDA-THF at negative 78 degrees, followed by the addition of formaldehyde and methanol and subsequent addition of heat. If you think you know what's going on with this lecture, I would encourage you to pause the video and come up with this mechanism on your own, and then when you restart, you can see if your answer matches mine. So here are the molecules at play in this reaction. And what the directions, what the specifications that I had on the PowerPoint slide communicate are that I'm going to first react the lithium diisopropylamide with this compound, and then after this is done, after I've let it react for some amount of time, then I'm going to add in the formaldehyde. Now, technically, I could do all of this in the same pot because lithium diisopropylamide is going to scavenge hydrogens from the alpha position. And there are 2 alpha hydrogens over here and 1 alpha hydrogen right there. Sorry, yeah. And even though I call these alpha hydrogens, what I mean is that they are hydrogens connected to the alpha carbon. Formaldehyde, which is the other reagent that I'm going to add in this reaction, has 2 hydrogens, but they're not connected to carbons. So you can't pull a hydrogen off of the carbonyl carbon to make an enolate. You have to pull the hydrogen off of the alpha carbon to make the enolate. So LDA is not going to react meaningfully with formaldehyde. Okay? But I'm still going to wait. I'm going to add the formaldehyde here in a second. So the first thing that the reaction tells me to do is to mix my LDA with this compound. Now, LDA is a kinetic base. It's extremely strong, but it's also very sterically hindered. So when it comes in, it's going to have a hard time getting to this hydrogen over here because the methyl group is going to make that difficult. And instead, it's going to pull the hydrogen over here off of the less sterically hindered side. So I've got definitely more hydrogens here than I need. So I'm going to get rid of that hydrogen because the LDA is going to have a hard time grabbing it, and these 2 hydrogens are equivalent, so I'm only really going to need to show one of them. So the LDA as a base will come over here and rip this hydrogen off. These electrons will fall down to make the enolate. Then the electrons will cycle up onto the oxygen. Formaldehyde has not yet been added to the reaction, so it's out of play. We end up with our enolate. Now this is not a reversible process. Now that's kind of a lie. All chemical reactions have some reversibility, but the equilibrium constant so overwhelmingly favors product that we can consider this to be reasonably an irreversible reaction. And so you let LDA mix with this compound until you get 100% enolate formation. This enolate is unlikely to react and plug into itself. And what I mean by that is normally, once you make the enolate, then the electrons are going to collapse down from the oxygen and push out through the alpha carbon, where the alpha carbon is a nucleophile, and they're going to seek some type of electrophile. But this is going to have a hard time plugging into that carbon right there because of steric issues, and also because all of these got turned into enolates. There's really none of this left because LDA so effectively enolizes all of your compound. So we add a 1-to-1 stoichiometric equivalent and convert all of our ketone into enolate. After that's happened, let me flip this thing around so that I can run the reaction left to right still. Then we pipette in the formaldehyde. The formaldehyde is unenolizable. You can't make an enolate out of this because it doesn't have any alpha carbons to attach hydrogens to. It's also an incredibly reactive electrophile, so this is going to happen very quickly. We're going to end up producing our aldol oxide. So the aldehyde has now this is a ketone. I really wish that we would be more specific about referring to these as ketol versus aldol addition reactions, but we were generic. So even though this is clearly a ketone, we're definitely going to refer to this as some type of aldol reaction. And then the formaldehyde just has 1 carbon right here, The 2 hydrogens are still hanging on to it, and I have the oxide ion right there. That got a little ugly. Let's see if this can clean it up. There we go. Okay, now in the next step, this needs to pull a hydrogen off of something. It's not going to pull a hydrogen off of the conjugate base, sorry, conjugate acid of LDA has a pKa in the ballpark of 36. So this oxide is going to stay right where it is until I add some other hydrogen source, because this is not going to be able to come over here and rip a hydrogen off of LDA. All right, I'm reading the reaction instructions one more time. Show a mechanism for the reaction of 2-methylcyclopentanone with LDA-THF at negative 78 degrees Celsius. So we're keeping this very cold. And then probably at that same temperature, it's assumed we're adding in formaldehyde in methanol. And that's what I was wondering. Because, like I said, this right here, that oxygen cannot pull a hydrogen off of the conjugate acid of LDA. It's not a strong enough base to rip hydrogens off of nitrogens. So what we're going to need is for this methanol to be the solvent and also our hydrogen source. And we've seen that before. Sodium borohydride uses methanol as a solvent and also a source of hydrogens. The Birch reduction, which you probably don't remember from first semester organic chemistry, also uses methanol as a source of hydrogens and as a solvent. So let's go ahead and put methanol on there. I did not delete. There we go. Man, I'm really running up against the not an effective use of space. I'm even worse on a chalkboard. I'll use all of one chalkboard just to write out one molecule and then have to draw the mechanism through the metal gaps that separate the chalkboards. Okay. So now we've protonated this thing. Okay, this is where things would stop at negative 78 degrees Celsius. But then the chemistry tells me that it was followed by addition of formaldehyde and subsequent addition of heat. So in the presence of heat, we expect the chemical reaction to go all the way through to the condensation step. The methoxide, let's draw these alpha hydrogens. There's one more alpha hydrogen right there that I haven't plucked off yet. And that matters. If there's not an alpha hydrogen, then all the heat in the world is not going to allow you to form the enolate that leads to the condensate. So I'm going to use methoxide right here as my base. It's about to do weird things here. We'll put the negative charge on there. Methoxide is present because I just deprotonated a methanol in the previous step, so now I've got some amount of methoxide floating along in solution. I'm going to use that as the base to pluck this hydrogen off. And this is a case where we can either show the electrons resonating all the way up through the oxygen, or we can just leave them right on the alpha carbon. Either way you show the mechanism is correct because it's just a difference of 2 different resonance structures. So instead of pushing the electrons all the way up into the oxygen enolate, the alternate resonance structure is to just put a carbanion right there at the alpha position. Whatever way you want to show it is up to you. I got a lot of stuff going on at that one carbon right there. Okay, now this negatively charged carbanion, which normally I show as an enolate, but this time just for the sake of variety I'm leaving here as a carbanion, will drop its electrons down to make a pi bond on this side and push off water, sorry, not water, hydroxide as a leaving group. Hydroxide is normally a really bad leaving group, but the solution is plenty basic, and so I can go ahead and push it off. And so our final product of this reaction now has a methylene group hanging off. Oops. And the hydroxide is gone. That also means that you have hydroxide present in solution, so if you want to use hydroxide in this base subtraction step, you definitely could have. So here's the full mechanism. This, again, would be a 2-pot reaction. In the first pot, we just add the LDA to the ketone to form the ketone enolate. And when we're done forming all of the ketone enolate, then we can add in the aldehyde as a separate step. This prevents the LDA from making two different types of enolates. It can only make an enolate with the thing that you put it in solution with, and that also prevents that mixed aldol condensation reaction because you only allow one type of enolate to exist. You add the aldehyde in the second step when all the LDA has already been used up to make the enolate, and then we heat the reaction up to go from the aldol addition to the aldol condensation reaction. So what have we learned today? Well, we talked about the aldol, big picture was the aldol addition and the aldol condensation reactions. Before we got to either of those aldol addition or aldol condensation reaction, we talked about the acidity of the alpha position on aldehydes, where the pKa was approximately 16 to 18, and ketones, where the pKa was approximately 18 to 20. I'll make sure that that's consistent with the notes that I have right there. Yeah, yep, 16 to 18, 18 to 20. Okay. And then we also talked about the kinetic versus thermodynamic enolization. So the reason that we wanted to think about the acid character at the alpha position of aldehydes and ketones was to think about what bases we could use to make enolates out of aldehydes and ketones. If the aldehyde, or especially the ketone, aldehydes are always have a hydrogen on one side, so you're not going to run into kinetic versus thermodynamic arguments because there's only one position for an alpha carbon in an aldehyde. The other position is occupied with a hydrogen. For ketones, they can have two different carbons, meaning that they have two different alpha positions, and then we have to worry about which side is actually going to make the enolate. And so for the kinetic position, we keep, this is cold temps and strong bases. And this is where we introduced LDA. For the thermodynamic, we had room temp or higher and alkoxide bases. Alkoxide bases, and that's RO minus or hydroxide. All right, so now that shows us, then we can get into the aldol addition reaction. And the aldol addition aldol addition is where you have an aldehyde, alcohol. So you can take an aldehyde or a ketone plus another aldehyde or ketone gives you an aldehyde or ketone alcohol. And these generally require cold temperatures to prevent the condensation reaction. And we looked at aldol addition reactions right here. This is the enolization. We form the enolate plugs into an adjacent carbonyl group, and then we protonate it, and we're done at low temperatures. As soon as you raise the temperature, then you go to the aldol condensation reaction. And so when we want to make notes on aldol condensation reactions, they follow the aldol addition when heat is added. Actually, it's not necessarily that they add heat, you just don't keep it cold. Fall at room temperature or higher, room temperature plus. And then we talked about strategies, home, and I'm out of room on this slide. The purpose of this slide is not to make a complete study guide for you, but to show you how I would generate a study guide. So I would then put some considerations of mixed aldol addition or condensation reactions. and you need to kind of talk about how we can cheat the system so we don't end up with a case like this. So we don't actually, if we add two different types of aldehydes together, you can end up with a variety of products that you don't want. So then we talked about how well we can use a ketone for one and an aldehyde without an alpha carbon for the other, or you can use LDA to completely enolize one and then add in the second aldehyde or ketone as a completely second step, so you only get one type of enolate. So that was kind of the considerations that we get to here with mixed aldol condensation reactions.